Okay, well, thank you very much for the opportunity to give this talk. I love giving talks like this. It's sometimes you have to do more than just math, pushing symbols. You have to know a little bit about history. So this talk is going to be a lot of history, not only history of math and number system, but basically what happened with that and how banks developed in Europe, and what we see today around the world. So I'm going to start off very quickly. You can see this first slide here. You have two men in a woodcut from the Middle Ages. This is an abacus. I don't know if you want to turn the light off, maybe. Let's see better. This is an abacus over here, and they use that for counting purposes. All right, when they had to do a lot of counting. So this man is probably performing calculations for this man, who appears to be. You can see him here with a quill, and then this is the inkwell, and you have the numbers 1, 2, 3, 4, 5, 6. I can't see 8 anywhere. I do see 9 and a 0. And then some fractions over here, what appears to be fractions. Right? So you can probably date this thing based on the fact that there's a 0, or maybe it could be a coin. I mean, it could be a coin. It's not clear, right? Because he put it right next to this other symbol that looks like a 7. So at any rate, this talk is the number 0 and the mathematics of finance in the Middle Ages. Now, so let's start off way back. It's not going to be that long, but we start off with base 60. For integers. It's called a hexadecimal system created by the Babylonians in 3100. Remember, the Babylonians did a lot of carving on stone, right? Stone carving. So you can imagine how much work this would be. To actually write lots of numbers on stone, you have to cut them right and put them all in the right place. You can see the numbers go from 1 to 59, and at 60, it's supposed to repeat itself. But what happens at 60 is you move the 1 over, and then you put a blank. Well, they didn't have 0. So instead of 0, they left it blank. So you can imagine someone who didn't know that would really have a hard time trying to figure out what the blank meant, because now for us a space is not a 0. A space is really a space, right? So they left it blank, and then they would continue. But you can see all the symbols. They're quite complicated, but they're all fine. Basically, if you're Babylonian, you can understand all this, and you can carve them all pretty nicely in stone and communicate. Can anybody think here of where we use base 60 today? The number 60. Happens a lot, right? Right? Time. Something else? There's some other place we use base 60 again. Yeah, angles, right? Degrees. That's a pretty standard one. Then there's base 8 systems, or an octal system. These are also historically they were used. Actually, King Charles II of Sweden decided to use them in 1716. It didn't stick, obviously, but he did decide to use an octal system for a while. There's various Aboriginal people in California, the Yuki people in California, who what they did instead was count spaces between the fingers, right? 1, 2, 3, 4 spaces, 5, 6, 7, 8. Why they didn't count on their fingers is not clear, but it could be because if you're an early settler in a region that's maybe full of animals, you might perhaps lose a few. And so you may not want to count fingers, you might want to count the spaces between. Usually the space always stays, right? But the finger doesn't. So it's possible. I don't know what the reason is, but it's a very interesting idea. And then there's Pamean languages of Central America, also in the highland desert of central Mexico, used a base 8 system. Any other uses of octal bases today? Can you think of those? Base 8. Yeah, computers. Somewhere else? You listen to music, right? Right. The octal scale, music, and so on. So we're still using this stuff, right? That was created by other peoples. And base 2 systems we thought would be something that was actually new with computers, but it's not. Apparently, Pingala, an Indian, about 400 BCE. Now, of course, this means before the Common Era, and CE means Common Era. This is replacing BC and AD in modern terms. And this Indian mathematician, well, I shouldn't say he's a mathematician, he's really more a linguist of sorts. Actually, in a Sanskrit treatise on prosody, which is a connection with the study of poetic meters, tresses, syllables, and other stuff, actually managed to distinguish 2 different classes, which we can associate with zeros and ones, and actually they work like zeros and ones. So they think that maybe he's the one that should be credited with the discovery of the binary system. His work, turns out, contains material in the Fibonacci number. And again, some of these, there's connection between long and short syllables. And the Fibonacci number comes into play in that, long before Fibonacci. But because this work was mainly an oral tradition and wasn't written down until much later, people couldn't find anything. But people that study Sanskrit knew it because the tradition was carried on. Where else do we use binary systems? This is obvious. Right here, right in the computers, everywhere, right? And decimal systems are the ones that, of course, we use now. And the decimal systems were actually used before. Look at Chinese numerals, right? 1400 BCE, the Chinese, the old ancient Chinese used that base 10 system. You go from 1 to 9, you have different symbols from 1 to 9. But 10, you're using a new symbol plus 1 and then 11, which is this one and this one. 10 plus 2, 10 plus 3, etc. You can write them all. And the hieroglyphs from 3000 BCE seems like they used also a base 10 system. Fascinating. And base 10 obviously is used because of the number of fingers in our hand. People could count easily way back when, right? Without using abacus. So the Hindu-Arabic system is really the following 10 numbers, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, and then addition of 0. And 0 does not occur for a long time. 0 was also defined by Villedieu, a Franciscan monk, about 1225 CE, and Sacro Bosco, which means holy wood, not Hollywood, but holy wood, right? You could call him Hollywood, remember his name, Sacro Bosco, and also known as John of Halifax, who lived more or less around the same time as Fibonacci. And this is going to come up. These three people actually come up in this story. Very important. And why it's called Hindu-Arabic is because the Hindu created it first, and the Arabics disseminated it. And then we got it from the Arabs. Right? This is basically the story in a nutshell. Negative numbers. Okay, first appearance. Looks like the Han Dynasty. Chinese got this one first. But again, it's not so clear because the ancient Indians also claim to have known it at the same time. Now look, so almost the same period. But China and India are really close, right? So you figure, oh yeah, so it must have been somebody across the border, went over the mountains and talked to them, and then who knows who did it first. The point is it was done in that area of the world. And then we're pretty sure about that, right? So again, you can't really say, but however, in 9 chapters on the mathematical art and an unauthored obscure work in Chinese, negative numbers are mentioned as distinct entities. Red colors are used for positive numbers. Black colors in the manuscript are used for negative numbers. This is the opposite of today when you're an accountant, right? When you're saying we're in the red by 50 bucks, you don't mean you got 50 bucks. You mean you owe 50 bucks. So it's the opposite of what the Chinese did, right? Which is kind of interesting. So totally opposite. So they knew about this. Now the Chinese could also solve problems such as 2 plus x equals 1 implies x equals minus 1 because they had the negative number, right? So they could actually say that, even though perhaps it didn't mean much to them. But however, they did mean something to them if they thought about it as apples. So how do you go from 2 apples to 1 apple? Well, you give away 1 apple. The giving away was a negative sign. They thought of that. Giving away, minus 1. I give away 2 apples, minus 2. I don't have apples. I give away 2 apples. I owe somebody, or maybe I'm down 2 apples, so I think of negative 2, right? So that's kind of neat. Then by 1000, the Persian and the Islamic mathematicians made the associations, which of course were made before, that negative numbers could be thought about as debt, positive numbers could be thought about as credit, and 0, once the 0 came into existence, could be thought about as the empty set. Well, not really. It's the cardinality of the empty set. Right? That's how we think about it. That's the way to think about it. You got an empty set. How many elements does it have? 0. We actually give it a number. We call it 0. Right? 0 elements. So 0 as a number could then be defined also as the average value of a positive number and its negative counterpart. The negative counterpart we chose to denote by dash x. It could have been anything else. It could have been alpha x. You could have denoted by anything, so long as you remain consistent in your notation. And by definition, x plus its negative counterpart would give this element 0, right? Well, because the Chinese and some people had this, they could do this. And since the average of 2 positive numbers is halfway between the 2 numbers, it was decided the number 0 should separate the positive numbers from the negative numbers. That's really cool. We never really think about that, right? We never really think about the fact that this guy is right between 1 and minus 1. Why did we put minus 1, minus 2 over here? Why don't we put it underneath here? Or diagonally up, down? Or why do we put 0 here rather than at the end? Well, you know, we never think about this stuff. But there was a lot of work for these people to realize that 0 apples means I have no apples, therefore 0 is less than 1. Obviously, I've had apples, I have 0 apples. 0 should be to the left of 1. And then 2, 3, 4, 5, 6, 7, 8, 9. Now, the Arabs, of course, wrote it the other way around. But the Italians, with Fibonacci, decided to write it the way we now know, from left to right, instead of from right to left. And because of this average business, you see, you put -1 and 1 here, then 0 is exactly in between. And 2 minus 2 is 0. And 3 minus 3 is 0. So therefore, you write these in this decreasing fashion, the negative numbers. So this idea became really cool with Descartes, who decided to make another axis. Now comes the Euclidean plane. And then with rationals and irrationals, you can actually find the position of points on a plane by means of 2 ordered sets of numbers. In Europe, however, people were really worried about negative numbers. They considered them absurd, no consequence. Some called them irrelevant, up to the 17th century. Even though Fibonacci had shown that debt could be associated with negative numbers. And therefore, there was a real application for negative numbers, and therefore 0 had a real application. Even though you couldn't think of it. If you're just somebody in society who just wants to make a living, you don't really think about the fact that you have nothing. You think about the fact that, oh, you have no, you think about the fact that you have nothing, but you don't think about 0 as describing that being, right? You have $0 or 0 florins or whatever. Now the story really gets cool with algorithmy. Actually, algorithmy sounds like that. And if you think of the word algorithm, it comes exactly from al-Khwarizmi, who was a Persian mathematician. Okay, the word algorithm derives from that. And here's a Russian stamp with al-Khwarizmi on it, celebrating his 1200th anniversary. 780, 850, we don't really know exactly when he lived, but we know he lived. And he's credited as being the inventor of algebra. And the reason that stuck is because the word algebra came from al-Jabr, which meant subtracting a number from both sides of an equation. So you have 1 plus x equals 1, you can subtract 1, get x equals 0. That procedure of doing that became part of what was called algebra. So you probably heard about it a lot. When you read the book, you probably saw the word a lot, and therefore you say, oh, that's the algebra book, right, where all this stuff goes on. And we think of it that way still, right? So on this book on the Hindu numerals. Now, the origin of the word itself is really cool. Where does 0 come from? So it comes from the word Cipher, right? Which is the same, has the same etymology as the word cipher, which of course means something totally different, right? We think of cipher, we think of something else. But remember, cipher is also the root of the word chiffre and cifra, which is Italian and French for digit, right? For number, which is really cool. And you say, wow, why do we use different words for this? So it came from the Sanskrit shunya, which really meant empty. Okay, so the Indians had 0. They don't know what to call it, so they figure, well, in fact, since it really has to do with the empty set in some sense, let's call it shunya, right? The empty set. That word then became Cipher, became Zephyr, and Saphira, right? All Arabic words, as time goes on. In Italian, because through trade and all that stuff, the Italians call it Zefiro. So Zefiro is pretty close to Saphira and Zephyr and Cipher. Very close, right? And Zefiro in Venetian, because they wanted to shorten things, right, made it bisyllabic, 0. You drop the FI, right? 0, which then was adopted by the French, and then, of course, it became universal eventually as 0. So that's kind of interesting. The whole etymology of the word 0 is kind of cool. Now, it likely went from being a placeholder. Now, you see a placeholder is 0. So in the old days, you would have had a 1, it would have had a space. Nobody knows what the space meant, but I mean, it meant that the people that created the space, they knew that it had to be something like a 0, but they didn't know what to do with it. And they would put a 0. Well, we actually put a symbol there to signify 0 as what's in that space. And if we move the 1 2 spaces over, we would get 100. But again, it would depend on some point of reference. So now we put 2 zeros. So it went from being a placeholder to a number, we think, with Brahmagupta, about 650 of the current era. He actually devised rules for the number 0, which is kind of interesting rules. Basically standard rules. Sum of 0 and a negative number is negative. Sum of 0 and a positive number is positive. Sum of 0 and 0 is 0. To your average person, this would mean nothing. Why would you even want to consider the fact that 0 plus 0 is 0? I mean, who cares, right? Okay, And the sum of a positive and negative is their difference. And that was cool. So that meant that they thought of 5 plus minus 3 as 5 minus 3, which is something we absolutely take for granted, right? We never even think about it. That's the same. But I mean, there was a rule that was created way back roughly 1,400 years ago. However, got into trouble with this one. A positive or negative number, when divided by 0, is a fraction with 0 as a denominator. So you see stuff like 2 over 0. You don't know what to do with it. It's interesting. There's no notion of infinity, right? None whatsoever. So they just thought, well, just leave it like that and see what happens. And 0 divided by a negative or positive number is either 0 or expressed as a fraction with zeros as a numerator and the finite quantity as the denominator. So they could have written it as 0 over 6, would have been 0 over 6, or actually 0. That was a good one, because how do you divide 0 into n equal parts? There's no way of doing it, right? It's 0, 0. So they had trouble with this. So they thought, well, 0 is a good way of doing it. There's no way of doing it. So they associate no way with 0. And so that's, but this one, of course, is a problem. And the last one, that 0 divided by 0 is 0, was really a problem, because now we know with the advent of calculus, there's no way that that can be true, right? You can't treat 0 like this. So basically, it meant that division by 0 was illegal, but we only found that out 1,000 years later with Newton and Leibniz when they created calculus. And you started dealing with stuff that you had to divide by 0 and 0 over 0 and, you know, L'Hopital's rule, right? It's crazy. We even deal with infinity with infinity, but they had no way of getting there. So there's a story connecting the word cipher to the word 0. Gosh, time goes by quickly. So like I pointed out, Cipher, the Arabic, Cipher, and 0. And basically, I sort of alluded to it. When you're trying to explain the notion of 0 to the common person, you're saying it has something to do with the empty set and the number of elements in an empty set. And the average person would say, well, why do you want to know what this, how many elements there are in an empty set? If I don't have something, I don't have it, period. If I have an apple, I can understand that's 1. I cannot understand what you mean by the number of elements in an empty set. So, okay, so basically the word went around that people, those guys, they talk about stuff that we don't understand. This 0 thing, right? The origin of the word cipher. So the word became something, anything that mathematicians spoke about that we couldn't understand became cipher, something that was really not clear. This is an apocryphal story, right? It's just, it went around and it's not really clear that this actually was true. But it's sort of possible that people spoke in such a way that people couldn't understand, and therefore it said, okay, they're really talking about the cipher thing and we really don't know what it means. So there's a connection between those two. And the etymology, of course, as we saw, is the same. 0 and cipher. As we saw, also cipher leads to the Cipher and Cifra, which also mean digits, as opposed to 0 in other languages. 0 was made commonplace in Europe by the appearance of works by Fibonacci and 2 other people, Villagier and Sacrobosco. This one is French, this one is English, this one's Italian, all around the same time. Books must be lying around by Persian mathematicians that these guys are using more or less the same time. It's fascinating. This bottom part is the beginning, chapter 1, line 1 of the book by Fibonacci, the 9 Indian figures. Now, this book was translated in 2002 from the original Latin. 1202 to 2002 is 800 years. We did not have an English translation of Fibonacci's work in 800 years. People grabbed parts of it, right? And they extracted them from the Latin to write a paper on. But an actual translation did not exist till this translation by Sigler, which he made in 2002, just in time to celebrate the 800th anniversary of the publication of the work by Fibonacci. Look at the numerals. 9876, all written backwards, because he's probably reading them from a Persian manuscript, right? He's not even writing them the other way around. He's reading the way he writes them the way he reads them. With these 9 figures and with the sign, look, sign, symbol, 0, in which the Arabs call Zephyr, any number whatsoever is written. And we will show this below. So he goes on to describe the number system, whole numbers, right? Positive and negatives, everything. Chapters and chapters, hundreds of pages. And he goes on with that. Now, other people, Villagier, as I pointed out, more or less the same time as Fibonacci. These are contemporary people, right? Villagier is a Franciscan. OFM means Order of Brother Minors, Fratis Minoris. And he writes a book called Algoritmo. Remember algoritmo? Algorithm, right? It actually gets translated as arithmetic. about 1220. And here's the first line of his book. Interesting. He puts the 0 right there, right? As opposed to putting it here, which was where we would like to put it. But he puts it there and it goes down again. Again, maybe they have the same source manuscript, right? If it's Al-Khwarizmi's book or if it isn't, we're not sure. But because in those days, you didn't necessarily write down your references like we do now. It was common knowledge, like the web. A lot of the stuff on the web is common knowledge. You just write it down without actually pointing out who did what. And then there was another book written by Johannes de Sacrobosco called Algoritmus. This was Carmen de Algoritmo, which meant the poem or the song about arithmetic. It's actually a long poem. If you look at it, you can see here, capital letters. So it's actually a poem about arithmetic. He's trying to explain it to the people that are reading it. He actually does a very good job doing it, because that book gets used for hundreds of years. And Fibonacci's work gets sort of lost because it was too advanced. Right? And then Johannes de Sacrobosco around the same time again, right? Which means, of course, holy wood. Don't put two L's there, right? Sacrobosco. These two people, interestingly enough, Villazier and Sacrobosco, were contemporaries, we know from the ages, from their dates, may have been friends because they were both math profs at the University of Paris. They must have known each other. They must have collaborated, right? I mean, just think about math profs here. Okay, some don't. Well, all right. But most of the time, you know the other person's existence, at least. And if someone is writing stuff on the Hindu-Arabic numerals that's really new, if the other one's doing the same thing, well, they must have talked. But we have no evidence of this, right? I mean, we're talking 800 years ago. This is a long time ago, right? That's long before the internet and telephones and all the other stuff that we take for granted now. But what's really cool is that Sacrobosco is a lunar crater named after him, namely this one here, the one with the 3 holes in it. I don't think it's true of Villazier, but Sacrobosco went on to write a lot of books in astronomy as well. A lot of stuff. These people did a lot of stuff back then. And so this book was used heavily in the universities of the Middle Ages, having undergone 12 editions in 33 years since its first printed edition in 1490. So remember, until 1490, you actually wrote books, scribes wrote books with a pen, right? And then the printing press comes into existence, bang, books get printed. Well, imagine having undergone 12 editions in 33 years. I mean, even today, this is a feat. Right? But this book was so cool that, in fact, there weren't that many editions. Here's an illuminated letter from an earlier manuscript edition, written by hand, of Sacrobosco's book. You can see a man sitting here and writing the actual Arabic numerals. See? 04. We actually recognize some of them. Right? Pretty cool. I mean, the point is that he's trying to teach people these numbers. Now you get into Fibonacci, aka Fibonacci, Leonardo Bonacci. Fibonacci means figlio di Bonacci. It's a contraction of figlio di Bonacci, which means son of Bonacci, right? Also called Leonardo Pisano, Leonardo of Pisa, blah, blah, blah. And of course, these are his dates. More or less, we're not quite sure. He's a contemporary of St. Francis of Assisi. Genghis Khan. I mean, you don't think of these two guys as having lived at the same time. Well, Genghis Khan is invading Asia, right? And sacking all these towns. These guys, they're writing a math book in Italy. Kind of interesting. It's anachronistic, right? But it's kind of interesting. And the Crusades are going on in the Middle East. So this is a very, very difficult time, politically speaking. And yet he just forgets about all that stuff and writes math, which is a lot of mathematicians do that today. You know, it's true. Even today, it's the same thing. And here, in fact, is an inscription. This is a page, a vellum page from one of his works. And you have here the Fibonacci sequence. Actually, this is a copy of his original work. It's Liber Abaci, which literally means a book of the abacus, actually written in 1202, and then copied after that until it was printed. Liber Abaci is not a book of the abacus, because abacus was thought of as calculating. Right? The abacus, the tool, became the actual act. So the book of the abacus was really to be interpreted as a book of calculation, as opposed to as a book on how to use the abacus. It has nothing to do with that. Right? Although you use the abacus in order to make the calculations, that was not what the book was about. Or, another way of writing it in modern lingo would be everything a medieval commerce student wanted to know, but was afraid to ask. Everything you want is in there. It's amazing, right? Everything you want. And the main tool, of course, was the abacus. Now, what's in there? Well, okay, I'm going to show you the next thing. Here's a typical Chinese abacus. It's really cool. You should get these things. I tried to get one for today, but I couldn't get my hand on one quickly. So this part is heaven, this part is earth. There's 5 beads, and each bead here is 5 and 5. And then so you have the units, the tens, the hundreds, the thousands, and so on and so forth. And you can write numbers very quickly. This is 6. So 6, you bring down a heaven bead, that's 5. 5 and 1 is 6. So you bring it down to the middle. This is the main dividing line here where everything is done. That's 6. 3, you bring up 3 beads to the center. That's 3. That's 6, 3. 0 would be nothing. No beads move. Right? 7 would be 5 and 2. Right? So you bring 5 heaven beads and 2 earth beads, and they make 7. And you go on like this. And when you add numbers, even a complicated number like this, with another number like this, we would normally be writing them all down. Line, carry, carry, carry. Crazy. Takes you 1 minute. With this stuff, all you do is you move the beads up and then you read the new number. And that's it. That's why the abacus was such a cool tool. Even now, it's a cool tool. Right? If you know how to use it, you can actually add, multiply, divide numbers very quickly. Oh, so, right. So this, I didn't actually read what I was going to do here. But basically, Fibonacci expands on Al-Khwarizmi's work in Liber Abaci, his book. There's quick acceptance by merchants in Italy, bankers, especially in the use of the number 0, because all of a sudden things made sense. I'm adding 10 and 10, I'm going to get 2 and 0 because of 0 plus 0 being 0. Ta-da! Brahmagupta, right? So this is cool. We've got these nice rules, and everything makes sense, and everything is true, and they can understand their own accounting procedure. And eventually it led to this double-entry bookkeeping that all the accountants in the world still use. All right? Kind of neat. Now, here's what's in that book, more or less. You can read the first parts of the book have to do with adding, subtracting, multiplying, and dividing whole numbers, and dealing with fractions. One part is on the buying and selling of commercial things. Right? So remember, he's talking to tradespeople. He figures he's probably going to get more publicity if he talks to tradespeople. An interesting idea, right? But of course, the book remained quite unknown for a long time. On the barter of commercial things, how do you barter skins with something else? Because that's what they were talking about back then, 800 years ago. The buying of coins and certain rules on buying coins and bartering commercial things. On companies made among parties. So, you can start a company. Let's do it. Yeah. Right? How do you do that? Well, Fibonacci was going to tell you how to do that. Well, we never think of Fibonacci as doing that because we don't really know what's in this book, this huge, hundreds of pages book. On the solution to many, these are math problems, that we call in false position. That's another word for saying trial and error. Doesn't work, try something close. Doesn't work, try something else. Trial and error. We still use it today, right? Classic. It was known to Fibonacci, and it was known probably much longer. That's earlier than Fibonacci. On the rule called El Khataim, which is really linear interpolation, right? Everybody here knows what linear interpolation is, right? Given in the middle, just draw a line and find out corresponding point. Solves problems. By which almost all problems of false position, he even knows almost all problems. He obviously knew of problems that couldn't be solved by linear interpolation, but he knew that a lot of them could be done, which was really interesting. On the finding of square and cube roots. Now remember, this is without a calculator. Square roots and cube roots he could find using these algorithms developed by the Arabs and probably the Chinese as well. And the subtraction and handling of binomials and apotums. Apotums are irrational quantities because the Greeks knew about irrational numbers, root 2, right? So these guys knew about irrational numbers. And on the pertinent rules of geometric proportions and problems of algebra, see, he actually writes down algebra and al-muchabaya, which is proportion and restoration, which was that word algebra, really bringing the restoration meant you restore, you solve for the variable in a linear equation. So this is Sigler's translation over here. This is the man who, for the first time in history, translates directly from the Latin, 2002. What do we find there? Okay, I don't want to spend too long here. But I'll show you what kind of interesting stuff he does that I never did in school. I don't know if you ever did this in school. Maybe in my math club you may have done it, but he's just going to write down the answer to this without going through the usual rigmarole that we go through when we learn how to multiply two-digit numbers. Let me show you how he does it. So 2 times 8, 16. 6 carry 1. So far, looks familiar. Now what does he do? Instead of multiplying 8 times 3, which is what we do, he does 2 times 4 plus 3 times 8. So 2 times 4 plus 3 times 8 is 8 plus 24 is 32. Carry 1 makes 33. Put the 3 down, carry the 3.
I'm actually writing down the answer here. 3, 6 are the last 2 digits of the answer to this problem, okay? Keeps going. 3 times 4 is 12, but I carried 3, so now I get 12 plus 3, 15. And the answer is 1536. This is cool. This is really cool, right? Because even today, who knows this? Not too many people, unless you've read some advanced arithmetic books, right? I mean, in school we didn't learn this. Nobody taught us this in school. This is nuts, right? Well, this is cool. Fibonacci knew this 800 years ago. Probably got it from the Persians, and who knows who got this idea, but it's brilliant, and it works, and you can prove it, right? And that's really neat. Now, so you think that's cool. Look at this, 3-digit numbers. And he has it for as many digits as you want. He just develops the whole idea. Let's say you want to do 1, 2, 3 times 4, 5, 6. So you start off 3 times 6, 18, carry 1. Right? Then you go again, you go crosswise here. 3 times 5, 15, plus 12, 27, carry 1, 28. 8, carry 2. So 8, 8 are the last 2 digits of the answer. That's pretty fast for the last 2 digits of the answer, right? Then what does he do? Then he goes along here, and he goes, okay, 3 times 5, plus 2 times 5, 3 times 4, sorry, plus 2 times 5, plus 1 times 6. All right, so that's the next digit. So that's going to give you what? 3 times 4, that's 12, 22, 28. I carry 2, makes 30. 0, carry 3. So 0 is the next digit of the answer. And then you continue. 1 times 5, 2 times 4, which is 5 plus 8, 13. What did I carry? 3, right, which makes 6 carry 1, right, 16. 6 carry 1, and then the last one, 4 with the carry of 1 makes 5, and the answer is 56088. That is amazing. These are 2 3-digit numbers, which of course would take most of us at least 30 seconds to do, right? But you can see that if you're fast at this, you can do this very quickly and just write down the answer. Again, Fibonacci, right? Strikes again. I mean, this is amazing. Cool stuff. Casting out nines. You ever wonder about that? Never learned that in school. Well, actually, I did learn in school. But most of the time, you don't hear about it. So what you do is you want to check an answer. So what you do is you add the digits of the first multiplicand, the second one, 4, 5, 6. You add them up. Then you add the product of the digits. So 1 plus 2 plus 3 times 4 plus 5 plus 6. And then you write down the sum of the digits of the answer, what you think is the answer. What you think is the answer. And then you reduce it modulo 9. So this gives you 5, 6. This gives you 11, 15. Minus 9 is 6, so 6 and 6. But 6 times 6 is 36. So 36 should be here, and 3 plus 6 is 9. So this is a 9. Now, if this is the right answer, the sum of the digits should add up to 9. So you go 5 and 6 is 11. 11 and 16. Let's see. Okay, put the line there. Go back. 6, 6, 9. And you get 27, which sum of the digits is 9. So it's probably the right answer. It's not foolproof, but if you made a silly mistake with a number, usually the digits on the right-hand side will not add up to the ones on the left-hand side of that X. So he knew this. All right? What he had before him when he wrote this book, we don't know, because he doesn't give references. Did he have Al-Khwarizmi? Did he have Chinese stuff? Did he have what did he have exactly in front of him when he wrote this? Right? It's interesting to know. And then another thing we find here is he does the casting out nines business for actually sums. But he writes the sums the other way. This didn't stick. 25 plus 49 is 74. He puts the sum on top. We put it in the bottom. Actually, we're so used to it, we couldn't imagine putting the sum on top. But in many medieval manuscripts, and they're doing calculations, the sums are on top. And unless you knew this, you'd be really confused. You'd say, they don't know what they're doing. Oh, they know what they're doing. Their notation's different, right? But they knew what they were doing. And Leonardo da Vinci did this stuff too. And when you first read Leonardo, you can't make sense out of it. But he's using notation from Luca Piazzolla, who comes later in the story, and from Fibonacci. So what else do we find? Addition, multiplications of fractions. This is weird. This is cool and weird. Look, 11 and 5/6. How does he write this number? He writes it at 1/3 space 1/2 space 11. Now, why is that? This is the way, because he loves unit fractions. Fractions with a 1 in the numerator. Why does he like them? Who knows? He liked them, right? So this is some kind of thing that he did. 1/3 plus 1/2, of course, will give you 5/6. And then 11 gives you 11 and 5/6. So when he writes 1/3, 1/2, 11, what he means is this, with plus signs in between. But you sort of got to get used to that, right? Because you go nuts. But eventually you can imagine that because he insists in writing all these fractions as unit fractions, it can be very long. But he does it anyways, because he's got lots of time, right? I mean, no VCRs, no TVs, no baseball, no, nothing, right? He's got lots of time. And another typical question that comes up in this book would be, if one solidus imperial, right, a unit of currency, which is 12 deniers imperial, so they knew how to exchange money, which is amazing. We never think of that way back then. These people who were exchanging money from country to country, is sold for 31 deniers pisan. How many deniers pisan should one obtain for 11 deniers imperial? So it's a very simple problem in algebra. The answer is 28 and 5/12, which of course he has to write like this, because we flipped the notation later on. How does he explain it? Well, what's going on is this. We have 12 deniers imperial are equal to 31 deniers pisan. We just write that, right? And then we say, so therefore 1 denier imperial is 31/12 denier pisan. That's just divided by 12. Okay, that's cool. Then you multiply by 11 deniers imperial, you get 31 times 11 times divided by 12, you get 34. As the answer. That's the way we do it now. This is simple. Here's the brilliance of this guy. He says, okay, basically what he's describing here is exactly what goes on in this little rectangle here. He says you put the imperial denarii here, 12. How many do you really want? 11. What's the exchange rate? 31. Then he says cross multiply. But he doesn't know what goes here until he cross multiplies and he solves for what's in the box, right? The x. He's thinking algebraically, completely, but he has to explain it to business people, tradesmen, merchants, right? So he's not going to write x and confuse everybody. He's going to say, what happens when I leave this stuff empty and I have to put a number here that makes this times this equal to this times this? That's the answer. That's what he explains here. And then, of course, he treats problems on selling pepper, cheese, rolls, goatskins, cloth, all the stuff that people did in those days. We replaced that with VCRs, cars, all that stuff today, right? But back then, that's what you thought about. Then you find, oh boy, it's already 1:45, holy smokes. You find the Fibonacci problem about rabbits, right? So how many pairs of rabbits will be produced in a year beginning with a single pair each month? If in every month each pair bears a new pair that becomes productive from the second month on. Basically, rabbits never die. You assume that. Otherwise, we have a different problem. These rabbits aren't dying. So let's assume we've got 5 rabbits here. What really 5 is the preceding set of 3 rabbits, because they don't die, so they come from the preceding, plus the new rabbits from the previous, from second month back, because every second month a new pair is born, right? So we have 5 rabbits, which must be the preceding 3 rabbits, which gave rise to the 5 rabbits, plus 2 extra rabbits that come from the number of rabbits, the pairs of rabbits rather, that were present 2 months ago. Because every 2 months they reproduce 1 pair. Okay? So 2 plus 3 is 5, and then 3 plus 5 must be 8 for the same reason. And then Fn equals Fn plus 1, Fn minus 1 plus Fn minus 2. We get the Fibonacci sequence. Not really new to him. It turns out this guy Pingala, like I pointed out earlier, had it done with by studying short and long patterns of syllables of a given length in Sanskrit. There's the Da Vinci Code. Of course, this appears in the Da Vinci Code. You all remember that piece of paper that she has in her hands and Fibonacci sequence. And believe it or not, there's a journal devoted only to the Fibonacci numbers. It's volume 50. It's been around a long time. What can you say about this number? Cool stuff. So there's a recurrence relation for the Fibonacci numbers. The relationship between the Fibonacci and the golden number, which was really important back then because it was known to the Greeks, is that the ratio of 2 Fibonacci numbers approaches this number, 1 plus root 5 over 2, an irrational number. The golden spiral is created by taking a golden rectangle, which is a rectangle whose ratio of the length to the width here, the longer side to the shorter side, is the golden number. And then breaking up this rectangle into smaller golden rectangles. Here, smaller one here, smaller one there. And you keep breaking this up, and these are just arcs of circles. These are just arcs of circles. The center here, center there, and so on. You get a spiral. It's called a golden spiral, which many people claim appears all over the world, right, in nature. It's not really clear, but some people claim that. Now, trade. Okay, I don't want to spend too much time on this, but it's an interesting part of what goes on. Like I said, his work creates a lot of activity in trades and commerce in the 13th to 14th century. The book definitely remains obscure. Didn't appear in print until the 19th century. It's amazing to think about the fact that even after the printing press, people didn't think about printing his book because there were these other books that were far better and understandable, right? The book by Villedieu and Sacrobosco, They were printed. But his book, well, it was too advanced. It really was too advanced for its time. It was only printed much later. The ideas led to the system of double entry accounting. I'm not going to get into that, but basically what it says, you got two ledgers, one for credits, one for debits. You record transactions in such a way that the amounts in each ledger are always balanced. So every time you buy something, it looks like you're losing money, but you're gaining the thing that you bought. So therefore it's an asset. So the stuff that whatever number goes there comes in here, and that way things should balance all the time. But the idea was an amazing idea in the Middle Ages, the whole business of accounting. And then as deals became more complex, this is 13th century, we get promissory notes. I promise to pay you back so much money at such an interest rate. They really talk like this 800 years ago, right? Bills of sale, orders, contracts to suppliers, all marked with a wax seal. Typical wax seals, right? Boom, boom, boom. They had to put these seals was a measure of authentication, right? How do we know that this came from the king? How do we know this is a real purchase order, right? This is in modern lingo, right? How do we know this is a real purchase order? And where's your stamp? Where's your signature? And here the seal is down here. So if this had been broken from the manuscript, nobody could have identified that it was authentic, right? So it was part of it. Commerce during the Middle Ages gets really cool when in Florence, over a 300-year period, the Medici family starts minting the gold florin. This is like almost 24-karat gold, almost pure gold, 500 years ago. The gold florin is like this. And as they minted this, they created the standard for all currencies. Well, they never knew it was going to happen, but they sort of knew. It became, and even today, gold is the standard for all currencies, right? You either buy American dollars, euros, or you buy gold, in which case you sit it and put it in your safe and you're happy because no matter what happens to the other currencies, you've got gold, baby. And gold is worth way more than anything else, right? So they knew this. This is incredible. One gold florin now is worth $200 US. All right, just remember the number. It's going to be really cool in a minute. So different currencies of the period were valued in comparison to the gold florin. And that's the brilliance of these Medici people. So what else happened? The rise of the guilds. These are sort of trade unions, guilds. There were guilds for every profession known. Barbers, shoemakers, craftsmen, blacksmiths, goldsmiths, and money changers belonged to guilds, right? And these guilds basically regulated what went on in that business. So barbers could charge, let's say, I don't know, $1 soldo for a haircut. They all agreed, oh, we all charge $1 soldo for a haircut, right? Just like the Medical Association does now in Ontario. And there's a Quebec Medical Association, and each one has their own rates for how much you charge a patient that comes in. It's the same idea. It's called differently. They call it Medical Association. But it's a guild in the Middle Ages, right? It's the same idea. The exchange rate between coins, some that contain silver, because some try to fool you, right? They try to pass off a gold florin for something that's really gold mixed with silver, right? Fluctuate as a function of market conditions and determined by various banks and influenced by the money changers guild. So these guys also directed how much money was worth. Renaissance artists belonged to the Guild of Craftsmen, not the Guild of Artists, the Guild of Craftsmen. So they were there with anybody else that worked with their hands. They were called craftsmen, right? So Michelangelo, Leonardo, Raphael, all their apprentices, they all belonged to this guild. They had to, right? They had to. And the Medici Bank, which is the next part, which didn't need much time, but anyways, which lasted a period of 100 years, flourished as the biggest, most respected European bank. Now, this is cool. This is by the family, the Medici family, which you may have heard of in passing if you watched, I forget the show on HBO on the Pope. Well, okay. Sixtus the Sixth, the Borgia popes, right? They talk about the Medicis there, and so you've got these people from the old man Medici, the founder of the Medici Bank in Florence, who died in 1429, 600 years ago almost, leaving. Look how much money he left. 180,000 gold florins, which in today's currency would be $36 million. I mean, it's enough for us. It's a lot more money for us. Imagine those poor guys back then. Like, this guy must have been like a superstar, right? I mean, you can never imagine. Even owning one gold florin would be impossible for the average person in Europe. They didn't. This is between tradespeople. All right, so he left that much. His son Cosimo takes over leadership of the bank. He turns out to be the patron of Donatello, Fra Angelico, all these famous early Renaissance artists in Europe. He opens the first ever public library in 1437. Thank goodness somebody did that, because otherwise we wouldn't have what we have now, you know, universities with open libraries. Usually these libraries were for exclusive use of nobility. Kings have their own libraries, and clerics. You have to be a priest or a monk or somebody that, and these people were the ones that actually, so this is a brilliant idea by his son Cosimo de' Medici, who opens up the first ever library, because that must have been a dangerous thing back then. You want to have people to learn about stuff that they would otherwise not know, which of course Machiavelli knew, who lived around the same time. Oh, you give people this power, you know, they're going to boot you out one day, which of course happened, right? But that's cool because there's progress, right? So this guy dies in 1464. His son Piero, son of Cosimo, who has a humanist education, which is a big thing going on in those days. You're really irreligious, so to speak. He inherits the bank and starts calling back loans. He says, I want your loan, I got your money, I want your money, I want your money. The result is these poor businesses, they have no money to do their business, ergo a recession. One of the first recessions that are chronicled, and actually Machiavelli mentions it, that people stop buying. And as a result of this son calling back these loans. That's a recession. That's exactly what we're in now, right? It's interesting. Then comes Lorenzo, called Lorenzo the Magnificent, right? He's like the great one. Son of Piero, turns out to be a hedonist, a tyrant, but a patron of the arts. He subsidizes all the arts, poets, whatever, musicians. He loves everybody. Anybody that's in the arts, money, you got money. Just do it. Just do what you do the best you can. So what he does is, this is the golden age of Florence. Now remember, he's called the Magnificent only because he subsidizes the arts. But in other respects, it's like horrible. He spends money from the bank as much as he wants, goes to the bank and says, this is my bank, so therefore I'm going to take out 10,000 gold florins this month and do whatever I want to do and subsidize these artists or whatever. To a lesser extent, he subsidized Da Vinci, but he really subsidized Botticelli and Michelangelo. We know now they did amazing works with money from Lorenzo. To a lesser extent, Da Vinci. Why? Because Da Vinci almost never finished what he started. And then Lorenzo says, what the hell am I going to give you money for? You're not going to finish what you're doing. Why don't you go play in Milan somewhere? You know, and he eventually took off to France. But I mean, because poor guy, he really didn't do much. He got a few commissions from the Magnificent, but he was not successful in running the bank, whose assets reduced noticeably during his reign. He died in 1492, which was the age of discovery, right? Columbus. The Rivers book, The Rise and Decline of the Medici Bank, opens up with a statement. Look at this. This is the first line of this book. Modern capitalism based on private ownership, which is exactly the way we think about it, has its roots in Italy during the Middle Ages and the Renaissance. This is the bank that basically started it all, right? The Medici Bank, which created all these famous artists. It's really cool. So very quickly, the Medici Bank opens up in 1397 with 10,000 gold florins by Bicci, the old grandfather or great-grandfather. They invest in wool factories. Brilliant! That's what people wear in winter. They wear wool, right? So people have to dress up and let's invest in wool factories. They made a fortune in wool factories. Other commodities like that. They opened branches in Lyons, in London, and in Bruges. Problems began when all three began loaning large sums of money to secular rulers who were notorious for being delinquent. They knew these guys weren't going to pay them back. But they figured, you're a ruler, you're going to pay me back. But they didn't. So what happens is the London Bank falls in 1478 with 51,000 gold florins in the red, followed by the Bruges Bank, and then mismanagement, bad investments, corruption led to the collapse of that bank in 1494, which is 2 years after the death of Lorenzo. Of course, he spent all the money anyways, right? We knew he took money out from the bank, and with all these collapses, with all these other people that were screwing around with the money. But look at this line: mismanagement, bad investments, corruption. Do you remember how this recession started? It's exactly how it started. Do we learn anything from these guys? No, we still do it, right? It doesn't matter. I mean, we still do the same thing. It's amazing. We haven't learned much. Okay, so this is about the double entry business. All I can say is that Luca Piazzolla, that I've talked about earlier in some other talk, and the Summa d'Aritmetica, now generally believed to be of earlier origins. This is what it is in Italian, registrazione in partita doppia, double column entry. Piazzolla basically does what Fibonacci does. They become diffusers of knowledge. They take all the knowledge that's known, and they write a book about it. Bang! This is what I know, right? And Piazzolla does the same thing. Again, they don't give sources. They don't have to, because this is common knowledge at the time. So some people claim that Piazzolla robbed and he plagiarized, but you see, those people don't understand the mentality of the period. He didn't do that. However, this guy, Amatino Manucci, we don't even have a picture of this poor guy. He flourished around 1275. Records from 1299 to 1300 for Giovanni Farolfi and Company. This is an Italian company that really existed in the year 1300, right? Makes use of the system. Some claim the Medici Bank under Giovanni, the old man, right, the older, made use of it as well. So if these guys knew about it, then he couldn't be the discoverer. But we know that Luca Piazzolla transcribed stuff, so therefore he isn't the discoverer of the double entry system, although every accountant you talk to will tell you that he is. But he isn't, but he's writing it down for posterity, and he's explaining it for everybody else. But we also know the Republic of Genoa in 1340 made use of the method. And others claim that the, here's another one, Bahikara system in India, through an old tradition, also predates all European discoveries by centuries, if not millennia. So they claim, because they've done a lot of contributions, that it might be that. Here's Luca Piazzolla, so on what appears to be a musician, by a rhombicubic octahedron. This is a rhombicubic octahedron. Sketched by Jacopo de Barbari. They're not quite sure if it's him, but if you looked at these two little gizmos here and a very cool rendering of this object, you would find that the artist actually sees light coming in and a building coming in through that, and he sketches the building. And he sketches the building, the other reflection on the other side. That's really cool, right? Too many people do that. But that's really neat. So there's Luca Piazzolla. And then Leonardo stuff from the five. Now, I got to talk about this before I end. You look at this stuff and you say, that's Leonardo, of course, right? So Mingarelli's talking, he might be talking about Leonardo. But you look at this and you say, well, this one doesn't exactly look like Leonardo. This looks like Leonardo stuff, right? All these drawings and the wind blowing here. And here's another one that looks like a wheel of sorts, a pinwheel. And something else here that it's hard to know exactly what it is. But you look at this stuff and you say, could be Leonardo, right? But who is it? It's not. It's a guy called Mariano di Jacopo detto il Taccola. We call it the Taccola, right? This guy dies in 1453. Leonardo was 1 year old. But look at this stuff. This looks like Leonardo's work, right? And even more interesting is this. Ba-bam, ba-bam. The one on the right is Leonardo's work. The one on the left is Taccola, right? These people became known as artist engineers. They could draw, and they were also speculators, right? They drew engineering things that nobody had ever seen before. And there's proportions here for the parts of the body. Leonardo doesn't put the proportions in, but he talks about them down here. And yet he stretches out the arms. Of course, a much better rendering than what Taccola did. But my feeling is that he had this. Yeah. Top right, yeah. Was what? Perpetual motion machine. Oh, cool. How do you know that? Right. Okay. Oh, yes, yes, of course. And so therefore it should constantly keep turning. That's a good one. That's very nice. That's cool. Thank you. That's wonderful. All right. Very good. Very good. So he had the idea. Yeah, that's really neat. I like that. Yeah. Okay, so here we have this part here. And so I think that Leonardo probably borrowed stuff from other people, right? And here's Leonardo's stuff in cryptography that I've talked about at other times. For example, words are reversed. Ingil in Italian becomes ligni, which is really ligni the other way around. And he makes a mistake with trova, trova, which is really trova, but he adds a U. So he tries to mislead people. He already writes the other way around, which is hard for most people to write. And Nilopanna, which means Napoli, which means to Naples. So you see that, you don't really understand what he's doing, but he's really trying to encrypt something. Very simple encryption rather, based on the reversal of letters. And he reminds himself to bring a blanket. How are you going to forget a blanket? You know, he freezes to death. There's a guy called Palladino. And I have to talk about Palladino. I know, I don't have much time. 1 minute. Maybe 5 minutes. But anyways, Palladino is one of those people who sort of goes in history and vanishes. You've heard of Palladino fonts, maybe, in Windows. Well, the first font that Apple ever used in their Mac OS was the Palladino font. This is the only time we hear Palladino, right? But who was Palladino? Palladino was an amazing man. I want to make justice to this guy because he was incredible. Giambattista Palladino, called the calligrapher's calligrapher. So well known among calligraphers. Born in Rossano, Calabria, more or less around 1515. Died in Naples in 1575. Definitely contemporary Michelangelo. They even knew each other. They had to, because he was the secretary of the Pope. So Michelangelo got his commissions from the Pope, right, from the Vatican, and so they're from the Medici family as well, then they had to have known each other. So who was Palladino? Palladino was probably one of the first really serious cryptographers. This is an example of one of his ciphers. Right? Look at this. I mean, look, A, B, C, D. This you think is a B, but it's actually a G. It doesn't even look like a G. And you think you got an O figured out when that looks like an inverted P. Right? It wasn't going to be easy to decipher this unless you actually had the method of decryption here. So he's one of the first serious cryptographers. And why does he do this? Because popes have to talk to leaders and they have to bring messages. There was no trains, no airplanes. They have to bring messages by horseback, one place to the other. So the message had better be encrypted so that if somebody intercepted it, so it doesn't make sense. But somebody at the other end had to know how to decrypt it and decipher it rather, and therefore you needed to do this. So since he was a calligrapher, he could make long ends on G's, and that long end meant something very specific to the reader at the other end. And he knew this. Now, why is this guy cool? Because he knew he could read, write, and calligraph in 29 different languages. 29! Basically every language in Europe and the Orient he knew by heart. This guy was amazing. Palladino, right? You need to know this about him because he was just incredible. Really exciting fellow, you know. We don't know much. So then at the end of Fibonacci, sorry. No. Gotta catch my breath. Fibonacci numbers, basically the basic fact, like I told you before, is that the ratio tends to the golden number, tau. That's very easy to prove. You just use the recurrence relation. You divide by Fn on top, right? So we have Fn plus 1 is Fn plus Fn minus 1. Divide both sides by Fn. Assume the left-hand side limit exists. We haven't proved that yet. But assume it exists. If it does exist, then it doesn't matter how you get to x, which we call the limit. Replace n by n minus 1. That has to give us the same limit. Replace, let's see. Oh, yeah. No, not quite. That's not what I was saying. Fn minus 1 over Fn. Yeah, that's the reciprocal, isn't it? This is x. Then 1 over x is Fn over Fn plus 1. And then you change n to n minus 1. Right, so this must be 1 over x. Okay. And therefore, x must be 1 plus 1 over x, which means that x must be the solution of a quadratic, which is 1 plus tau. Another fact that's not obvious to prove is that pi is actually equal to this number involving the Fibonacci numbers, the odd Fibonacci numbers. That's strange, very strange. All I can show you here is that you can use the ratio test in order to prove it, that it converges. To prove that it converges to pi is actually hard to prove, right? But that's basically it. And finally, I did it just in time, a great disclaimer by Fibonacci. I love this disclaimer. He puts this in his book, right at the end of his preface. Before he started reading chapter 1 and go crazy with this new system of numerals, he says, if by chance something less or more proper or necessary I omitted, right? Now it's me. Your indulgence for me is entreated. I'm asking you, right? As there is no one who is without fault, and in all things is altogether circumspect, prudent. So this is the end of my talk. Thank you very much.